Welcome to the tutorial on construction of state diagrams. One of the most challenging part of the sequential circuit synthesis is the development of the state diagram from a verbal or a written problem statement. The translation of a problem statement into a state diagram may require several attempts before the final state diagram is reached. So a construction of a state diagram in sequential design is analogous to the construction of a truth table in the combinational logic design. So here we will present several problems for which we will construct a state diagram prior to continuing the design of a complex circuit. So mainly we will look into three concepts, that is the up and down decade counter, sequence detector, and third one is serial XS3 to BCD code converter. So to begin with the first concept, that is the up down decade counter. So here we create the state diagram for a synchronous decade counter. The counter is to count up or down in binary depending upon the value of the mode control input signal. When the mode control input signal m is equal to 0, the counter is to count up, and when m is equal to 1, the counter is to count down. The counter is to repeat or cycle, that is to count from 0 to 9 and then start over if m is equal to 0, and it is supposed to count from 9 to 0 if m is equal to 1. The counter outputs are of two types, y and z. So the counter output y will be equal to 1 if it is counting upwards and the terminal count is reached, whereas the another variable z corresponding to the counter output if the counting down operation results and the terminal count is reached. So as you can see from this particular diagram, we have a total of three variables, m, y and z. M corresponding to the mode control, y corresponding to the counter output, and also z corresponding to the counter output. Now if the mode control value changes during the counting sequence, the outputs y and z will be asserted, that is it will be equal to logic 0 when the terminal count is reached. So we can develop the state diagram for the up down decade counter as follows. Since it's a decade counter, so we require a total of 10 state symbols starting from 0 to 9. Then we need to determine the mode control value, whether mode control value m is equal to 0 or whether the mode control value m is equal to 1. If the value of m is equal to 0, then we need to count in the upward direction. If the value of m is equal to 1, we need to count in the downward direction. The next step would be to connect each state symbol with a directed arc, as you can see here, indicating the next state for the two values of m. So if you can observe, m is equal to 0 is indicated as m dash in this particular diagram, and the arc is directed in the upward direction, whereas m corresponds to m equal to 1 and the arc is in the downward direction. So if you look at the state diagram, we have upward direction counting from 0 to 9 and a downward counting direction from 9 to 0. To indicate the outputs for up counting, we have m dash slash y, and for the downward direction we have m slash z. So clearly the state diagram that is being specified is a Mealy machine because the two output variables are dependent on both the mode input signal and the present state. So this is with regard to the up-down decade counter. Next we have, under the construction of the state diagram, a sequence detector. So here is a numerical which says we need to construct a Mealy state diagram that will detect a serial input sequence of 10110. The detection of the required bit pattern can occur in a longer data string, and the correct pattern can overlap with another pattern. When the input pattern has been detected, it can cause an output Z to be asserted high. So in order to understand this, we will consider an example of an input string meaning input sequence, which is given by the variable X, and Z corresponds to the output. So the input string or the input sequence is considered to be 10110, 110110, and then we have the output, and this is just an example which has been taken. So to begin with, so from this example itself, we know that the serial input sequence is 10110. So once the sequence is detected, Z, that is the output variable, will be equal to logic 1. Otherwise, it won't be equal to logic 1. So in this particular solution, we have the input variable X. A single output variable is used to indicate the detection of the correct input pattern. If incorrect pattern is presented, no output occurs. So to begin with, we will consider the first initial condition or the initial state to be A, and we will check if the input is 1 or 0. If 1 occurs, then the machine will change its state from A to B, and if 0 occurs, it will remain in the state A itself for the first input 1. Next, to check the second bit. So we have finished this much part of our transition, A to B, A to A. So when we move to the second bit, we need to check if the second bit is logic 0. If the second bit is detected, the machine will go to state C, else it will remain in the same state. So basically, if you observe, from what we understand is that if the variable is detected, then there is a transition to another state. If not, the transition will occur within the same state. So that is what has been indicated here. For the second bit, if the bit is equal to 0, then you make a transition to state C. If not, you make a transition to state B itself. Now we will be checking for the third bit. For the third bit, you have completed till here. That is, you have made a transition from B to B and B to C. So when checking the third bit, a transition from C to D occurs if a string of 101 is detected, whereas if a string of 100 is detected, the machine will go back to state A, because a 100 string cannot be a part of the correct input string. So for the fourth correct input bit in the serial string, that is 1 here, we are going to check for the transition from D to E or to C. If it is to be considered, state D will indicate that the 3 correct input values have been received. So that is 1, 0 1. So when you are in state D, it means that the 3 correct input values have been received. So if I have to mark, then I can say that these 3 values have been correctly received when I am in state D. Now from state D, when you are checking the 4th bit, that is for this bit, if x is equal to 0, that means if input x is equal to 0, then you are going to move back to state C, indicating that 2 correct inputs have been received. That means 1 and 0 have been correctly received. If x is equal to 1, then you will move to state E, which will indicate that you have received 1, 0, 1, 1 correctly. So that means you have received 1, 0, 1, 1 when you are in state E. So next task would be to check for the last bit, that is input bit in the serial input sequence, that is the 5th bit, whether it is logic 0. Now for that, what we are going to do is, we are going to see where will be the transition of E towards B or either to C. If x is equal to 0, the output will be logic 1 and the state will change from E to C. The reason for changing from state E to C is that the string can overlap. The string can overlap, and we can say that we have correctly detected 1, 0 of the new machine. That is because if you look at this particular example, you have a 1, 0 here. So if you are in E and you get a logic 0, then you need to move towards state C. If you get a logic 1, then the machine will change its state to B, indicating that you have received the first one of a new string correctly. So from this example, what we clearly understand is that initially we will be checking for the first 2 conditions, first 2 bits. After that, we also have to check for the previous bit patterns before jumping into a next state, and check also the output variable z, whether it is asserted high or low. To better understand, let us look into further examples and we will be easily able to get through this particular understanding of how these numericals are solved. So here is another example which says, with a suitable example and appropriate state diagram, explain how to recognize a particular sequence. We can assume any sequence, but in my case I have assumed this sequence 1, 0, 1, 1, and the state diagram I am considering to be having a single input variable which I will represent as x and a single output variable which I will represent as z, and z will be equal to 1 if the correct sequence is detected. So if you observe, the correct sequence in my case from what I have considered as an example, it has been present in the input variable 1, 0, 1, 1 here, and once that sequence is detected, z will be equal to 1, and then again I have another correct sequence here and z will be asserted. So 1, 0, 1, 1, again z will be asserted. So you can see that there's a repetition and you can see the number of times z is being asserted. So to begin with the initial condition, I'm considering that initially for the first bit I'm in the state A, and if the input bit x is equal to 0, I'm going to make a transition to the next state, that is B. If it is going to be equal to 0, then I'm going to remain in the same state A. When I'm going to check for the second bit, I'm going to check if the second bit is 0. So if it is going to be 0, I need to make a transition to the state C. If not, I will have to make a transition to state B itself. Now when I'm going to check for the third bit, I need to check for the previous patterns as well, that is 1 0. Okay, so I need to check for the previous patterns 1 0 and then check for the third bit. So if I have it as 1 0 and the third bit to be 1, then I will move to the state D. If not, I will move back to the state A. So this flow goes in the similar manner like the previous case. So you will be returning back to the initial state A, indicating that the pattern has to be detected from the beginning. Now when you're checking for the fourth bit, that is the last bit, you need to observe what are the possible changes. So let me consider the sequence. When you are in state D, it implies that the sequence 1 0 1 has been correctly detected. That is, the first 3 bits are correctly detected. Now when you want to make a transition or check for the fourth bit, you need to check whether the fourth bit is equal to logic 1. If the fourth bit is equal to logic 1, then you need to change from D to B. So this will indicate that the first bit is already detected. If the fourth bit is logic 0, then you will make a change to state C, indicating that the first 2 bits, that is 1 0, have been correctly detected. So this problem or this numerical is very much similar to the previous one, wherein we are trying to identify or recognize a particular sequence from the bit string that is being provided. So moving on to the second type of the numerical under sequence detector, they have specified that we need to design a mealy state machine that can detect a serial string of 4 inputs where each input is a 4-bit code, and if the string of 4-bit code is correctly received, then an output is to be generated. An incorrect input code pattern is to generate a second output, and the second output is to be generated only after receiving the sequence of 4-bit codes. So in this particular numerical, let us assume the input combinations to be 0 1 1 0, 1 0 1 0, 0 1 0 0 and 1 0 0 0. Now if the first pattern is correct, then the state will change from A to B. If the code is incorrect, then the change is to state C. So I have considered the input combination of 0 1 1 0 in this case as the starting point. If it is correct, I have to change from A to B. If incorrect, it has to move to C. Now coming to the second code, if the second code, that is 1 0 1 0, is correct, the state will change to D, that is from B to D. If it is incorrect, then the state will change from B to E. Any input combination can cause a change from state C to state E. That is why if you see here, 5 star will indicate all input combinations will cause a transition. So any input combination can cause a change from C to E. Next, if you see, the type of the sequence that we had was 0 1 0 0. So we had completed till here. So for 0 1 0 0, if the third string is correct, then the state change will occur from D to F. If it is incorrect, it will change to D to G. Again, if the state is E, any input combination can cause a change from E to G. That is why again we have indicated it with the 5 star. That is, all input combinations can cause a transition. So the next set of input combination that we had was 1 0 0 0. So you were in F, and now if F, that is the fourth string, is correct, then the output open is generated and the machine will start searching for the initial condition. That is, the state changes from F to A. If it is incorrect, then the output alarm is generated. So the state will change or will be changing to A from F and also from G. So from both these conditions, if output 1 0 0 0 is incorrect, then from both F and G you are going to move to state A. So in general, a pattern detector like this can be used as an electronic combination lock that will open when the correct combination is received and turns on an alarm if an incorrect combination is tried. So if you can see, because from F you had a correct combination, you moved to A, but incorrect combination you will move to A, but also you will have an alarm that will sound which will indicate that an incorrect combination was tried. So let us move into the next set of numerical. So here we have to design a milli serial bit pattern detector which will detect the sequence 0 1 0 1 0 in a longer bit string. If the pattern is detected, it will cause the output Q to be active high. If a pattern of 0 1 1 occurs within the same serial data string, it will cause P to be active high. If 0 1 1 bit pattern occurs, it will cause the state machine to initialize and start over looking for 0 1 0 1 0 pattern. Overlapping 0 1 0 1 0 patterns can also occur. So they have given the example and we need to find a solution to this problem or draw the state machine. So from the question, what we understand is that if a pattern 0 1 1 is detected, then P is supposed to be high. So 0 1 1, P is high. Similarly, you have a pattern of 0 1 1 here and P is equal to high. Also, you can see that if an input sequence 0 1 0 1 0 is detected, then Q is equal to I. So 0 1 0 1 0, that is together you have Q to be equal to high. So 0 1 0 1 0, Q is equal to high. So again, if I consider this sequence, again you can see that this will be equal to high. So let us begin with the design. So we will look for the first bit. If the first bit is equal to 0, then you have to make a transition to the next state. If not, you need to make a transition to the same state. Then we will check for the second bit. So this would be the same repetition. If the second bit is equal to 1, you will make a transition to the next state. If not, you will make a transition to state B. Mainly, we need to focus on this particular input sequence, this bit sequence, that is 0 1 0 1 0. So based on that, we are drawing the state diagram. So next we'll go to the third bit. So as per our bit pattern, our third bit, if it is correctly detected, it is supposed to be 0. So till here it would be the same thing, A, B and till C. Now we need to look for 3 bits, that is 0 1 0. If 0 1 0 is correctly detected, then you go to the state D. If not, you go to the beginning, that is state A. So that is why you can see that here we have specified it as 1P, because our third bit is supposed to be logic 0, and if our third bit is logic 0, then we have a transition to state D. If not, if it is equal to 1, that means we have detected 0 1 1, which will indicate that P is equal to high. So that is why you can see that when you consider input to be is equal to 0 1 1 slash P, you will make a transition to state A. Then we will be checking for the fourth bit. So fourth bit, whether it is 1 or 0. Now you are in state D. So when you are in state D, this will indicate that you have correctly detected 0 1 0. If you have correctly detected the fourth bit to be equal to logic 1, then you make a transition to the next state. If not, you make a transition to state B, indicating that you have correctly detected the first bit. Now while checking the fifth bit, that is the bit 0 as per the input sequence. So you are in state E now. If the bit is 0, you will move to D and you will conclude that Q is equal to 1. The entire sequence has been correctly detected. If not, you will move to A, indicating that you have correctly detected 0 1 1, because the last sequence that you could see was 0 1 1. So you have correctly detected 0 1 1. So these are the two transitions that you will make for the fifth bit. So this is the same repetition of the previous two problems that we have seen, except that in this particular case we had an extra pattern, that is 0 1 1, for which we had a logic high that had to be marked in the circuit or in the state diagram. So this is the complete state diagram for the bit pattern that has been shown. Moving on to the third concept under the construction of state diagrams, that is serial access 3 to BCD code converter. So again here we will look into the numerical directly, and the question says we need to design a melee state diagram for a circuit that will convert a serial access 3 code data, that is input X, into a serial binary coded decimal data BCD, because both XS3 and BCD are 4-bit codes. The machine is to return to the beginning after 4 bits, input the least significant XS3 bit first. The serial BCD data input is labeled P. If any non-XS3 input sequence occurs, it should cause Z to be equal to logic 1, and the data are serial, so a sequential circuit is necessary to accomplish the conversion. To begin with, what I'm going to do is I will first draw a table which shows the XS3 to BCD conversion and then begin with the state diagram. Now, in the question, clearly it has been mentioned that we need to focus on the LSB bit of the XS3. So if the XS3 LSB bit is 1, then BCD bit will be equal to 0. If XS3 LSB bit is 0, then BCD bit is equal to 1. So let me consider input to be X and output to be BZ or Z, because it is mentioned that serial BCD data input is labeled as B. So BZ because it is a BCD and Z because it is an output variable, so it is represented as BZ. So I am considering the initial state as S0. If LSB bit is 1, BCD bit is 0. If LSB bit is 0, then BCD bit is 1. In this particular case, X, as I mentioned, is an input, B is the BCD output, and Z is the non-XS3 input sequence. If it occurs, it is supposed to be equal to 1. So that is why if you look at the state diagram, everywhere we have X/BZ. Since all the variables in the state diagram specified are XS3, that is why Z will be 0 throughout. If it is a non-XS3, then only Z will be equal to 1. Now, with the first state S0, if XS3 bit is equal to 0, the BCD bit will be equal to 1. If XS3 bit is equal to 1, the BCD bit will be equal to 0. So that is S0. The second XS3 input bit causes a transition from either state S1 or to S2 to some new state. So this process will proceed. So if I consider this to be S1 and this one to be S2, from S1, again if it is a 0, you can have a transition to 0 itself, and if it is a 1, you can have a transition to 1. Or if it is a 0, it can be 1, or if it is a 1, it can be a 0. So to observe as to how we have got this, we need to look into the truth table of the XS to BCD conversion. So from the truth table, when we were looking into the LSB, from 1 to 0 there was a transition, from 0 to 1 there was a transition, and this pattern was repeating itself. But whereas when you go to the second bit, you can see that you have a transition from 1 to 0, you have a transition from 0 to 0, you have a transition from 0 to 1, you have a transition from 1 to 1. So from S0, that was the LSB, you have moved to S1 and S2. Now from S1 and S2 you will have 4 different combinations, that is you will have 0 to 0, 1 to 1, 0 to 1 or 1 to 0. So this way you will have 4 states, S3, S4, S5, S6. Now next what you need to do is, in a similar manner, you need to look for the third bit in each case. So when you look for the third bit in each case, you can still have 0 to 1, 1 to 0, 0 to 1 and 1 to 0. Similarly 0 to 1, 1 to 0, 0 to 0 and 1 to 1. So this split up occurs in the case of the third bit. So moving on to the fourth bit, from there you need to observe what are the different combinations or the transitions that can occur from S4, S5, S3, and you will note that the transition from S4 and S5 are identical and hence can be combined. So states S6 to S11 will indicate the reception of the third BCD input bit. So after the fourth bit, all the states must return to S0. The output from the final state transition back to S0 will depend on whether a correct XS3 value has been received. If the fourth XS3 bit is incorrect, then Z will be equal to 1. So in order to check this, we are going to check the accuracy. So we will consider a sequence 0101 as the input, and we will see the sequence of states and the resulting BCD output. So if the input bit is 1, you will make a transition from S0 to S2, and BCD output will be 0 and Z will be 0. Next, if the bit is 0, you will make a transition from S2 to S4. BCD output is 1, Z is equal to 0. Next, we have the input bit to be equal to 1. So you will make a transition from S4 to S9. BCD output is 0 and Z is equal to 0. Next, if the input bit is 0, you will make a transition from S9 to S0 with BCD output 0 and Z to be equal to 0. Now let us also check the error bit Z that should be set when a non-XS3 4-bit sequence is attempted. So let us have the input sequence to be, say, all ones, which is basically a non-XS3 code. So when we have such sequence, from S0 we will move to S2, from S2 we will move to S5, from S5 we will move to S11, and from S11 we will move to S0. But in this particular case, if you observe, Z will be equal to 1 for the last case, that is S11. So here Z is equal to 1, which indicates that it is a non-XS3 code that has been attempted. So from this examples, it is very much clear that it is possible for us to recognize the pattern and identify whether the code conversion that has been done is accurate or no.